In this video we'll be taking a brief look at transistors, what they are, how they're made, how they work, and some of the uses we can put them to. Transistors were actually accidentally discovered in 1947 by a couple of guys who were trying to work out just how a p-n junction diode operated. And ever since then, that was probably the beginning of the silicon revolution. Everything, all the computer chips and everything can almost, the history can be started from this particular point in time. So just as a recap, remember that we have two types of semiconductors, an N-type, which has an excess of electrons because of our doping material, which has 5 valence electrons, and our p-type, which has a gap in the covalent bond due to the doping material only having 3 valence electrons. A bipolar junction transistor, as they're called, or a BJT, consists of 3 regions of doped semiconductor, either an NPN or a PNP. The devices are thought of as a current amplifier, having many applications for signal amplification and for switching. So their basic layout is something like this. We have NPN, and we call that an NPN transistor, where the P junction is the base, is in the middle, controls the flow of current through the device. A PNP transistor, on the other hand, has an N junction or type material in the middle, and it controls the current through the device. Now, although physically how they would be made is like this, the center leg of a transistor isn't always the base. It can be determined or changed depending on how the manufacturer wants the legs to come out of the package that they're in, as we'll see in a minute. These are the symbols, NPN and PNP. The way I remember the difference is an NPN transistor, right? The arrow is pointing out. In other words, the arrow is never pointing in, and the other one's the other way around. Transistors can come in various packages and various sizes, from a surface mount device, a tiny little thing here, only 2 or 3 millimeters across, right to big devices here, which can be 50 millimeters across. They normally have 3 legs, except some of them, if they've got a big metal case, might have 2 legs, and the case itself forms one of the connections. How do we find out, or can we determine whether a transistor is a PNP or an NPN? Well, we can with a simple little multimeter. If the multimeter has a semiconductor testing range, and that's a place where a range that is indicated by a diode symbol. And so if we put our meter onto the semiconductor testing range, put the positive or the red probe, the common probe, no, not the common, the positive, onto one leg of our transistor, and then the common leg, the negative, we switch between the other 2 legs and see if we get a reading other than infinite resistance on any of those legs. So, for example, if we have a positive, or our red lead is on one leg, and we get a reading on both the 2 other legs, that tells us that the base region is a P for positive, because we've got the positive leg on it. And of the other 2 legs, one will have a reading slightly higher than the other. For example, one might be 567 and the other be 569. The higher reading is the emitter. So in this case, if that was 567 and 569, it's a PNP, that's the base, that's the collector, and that's the emitter. And all we have to do is keep juggling around our leads until we find that we keep one lead still and the other 2 legs give us a reading, or give us 2 readings. So for a PNP transistor, we would keep the black lead still on one of the legs and move the red lead between 2 legs and get readings. Now, as with a diode, the readings we get is what the multimeter is telling us is the forward bias voltage of that particular junction. So it's normally So if your multimeter says 637, that's telling you that the junction forward bias voltage is 0.637 volts. Some multimeters don't have the point there, they just tell you 637. Others will have a decimal point to tell you what that it's actually a voltage. Transistors in a circuit are normally in one of three conditions. They're either cut off, in other words, current's not flowing, and that's like a switch turned off, or they're in what's called saturation, when they're fully turned on and there's a large current able to flow through them, or they're in an active region somewhere between off and on, where we can use them as an amplifier, or they're slowly turning on or slowly turning off instead of instantly turning on and instantly turning off. Now, a data sheet will look something like this, and what we're looking for is, for example, these readings here, the collector emitter voltage. So what's the maximum voltage that we can have between the collector emitter? What's the maximum voltage between the collector and base and the emitter base voltage? And also we want to also know what's the maximum current that the transistor can handle and how much power it can handle. We would also, the data sheet, if we're able to find it, would tell us what the pinouts are and what it looks like physically. We can also, when we're using transistors in a amplification mode, we can find out how good an amplifier they are by a test or by looking up their data sheet to see what their gain is. And their gain is given the symbol beta, and it's sometimes known as HFE or H(fe) like this. And what it is the ratio of the collector current divided by the base current. So under normal circumstances, our base current normally has about 5% of the collector current. So our total current, 100%, will be coming up will be flowing through the emitter circuit, and 5% of it will be in the base circuit, 95% will be in the collector circuit. And that from that we can, from the amount of current for each of those, we can work out what the gain of the transistor is, which is we need to do when we're looking at amplifiers in particular. Our little multimeters often have a place like this or like this. When we select HFE, or the gain for our transistors, here's it over this one, but it's related to this thing here, we work out where our legs of our transistor are, poke them in the appropriate holes for an NPN or a PNP, and our little multimeter will tell us what the gain of the circuit is. We can use the transistor as a switch, although it's not the best because it's not always fully on or fully off, but it can be like a switch. So in this configuration, where the base, for example, is tied physically down to the emitter or the 0 volts line for a NPN, our transistor is turned off. For an NPN transistor to be turned on, the base needs to be at least 0.6 of a volt higher than the emitter to have current flow in our base emitter circuit. In saturation, where our transistor is turned fully on, our base circuit is normally connected through a current limiting resistor up to the supply voltage. And in that case, it's fully on, conducting as hard as it possibly can. So what you're going to do in the lab is make up a little circuit like this with one of the transistors, and going to then connect it to the supply or the negative and see which what makes it turn on. We're going to confirm our theory that for a NPN transistor, the base needs to be positive with respect to the emitter, so NPN, positive. For a PNP, the configuration would be around the other way, with the emitter connected to the positive supply, the collector to the negative, and to turn it on, our base would also be connected to the negative. In that case, for a PNP transistor, the base needs to be more negative than the emitter. Various applications. We can use the transistor as, for example, a switch. We can connect it to a light sensing circuit and either have it turn on when it's light or turn on when it's dark. We could have it some sort of a float level switch, some sensor when something gets to a certain point, a level or height, like water, for example, we could get it to turn on. We can make touch switches out of it. And all sorts of little switches. We can make small circuits out of transistors. Because our basic transistor isn't a particularly good switch in that it's sometimes floating sort of part on and part off, there is a configuration where we put two transistors together like this, where the emitter of one goes directly into the base of the second one, and this is known as a Darlington configuration. And what this does is it makes the gain normally beta 1, or the beta of the first transistor times the beta of the second transistor. So we get a huge current gain. And in a simple circuit like this, we could have a set of contacts, and just bridging them with our fingertip is enough to turn the LED on in this particular circuit. So Darlingtons can be made with two individual transistors, or they can come in one package. So they only have 3 leads out instead of 6. And they like that, and they normally have, this is the normal symbol for a Darlington transistor. So that's a very brief overview of transistors. There is a lot of information on the internet about transistors, so there's a lot of references. You might want to pick one or two and go and have a look at them. All About Circuits is a very, very good, very good textbook or online about basics of transistors, etc. It's a very good one.